Let's imagine a scenario where you have a fair coin. Flipping the coin either gives you heads or tails with an equal 50% chance. On your computer, you also have a random picker. You give it how many cases you want, and it randomly selects one of them, again with an equal probability. Say we wanted to program our coin into our computer using this randomizer. Well, we first need to figure out how many cases we want, which for a fair coin is obviously 2. It becomes clearer when you turn the 50% into a fraction, that is 1/2, or 1 out of 2 cases. For the sake of simplifying our program, instead of using letters A and B, or heads and tails to represent the output, let's use binary numbers. This means that to encode our fair coin into a binary system, we would need just 1 bit of information. Now let's look at an unfair coin this time. Imagine this coin is biased towards heads, say with a 75% chance, and of course 25% chance for tails. If we want to encode this coin, we would have to count our cases again. Your first intuition would be to probably assume that we also have 2 cases here, which technically we do, but the fractions say otherwise. If we follow the same method as before, we would see that we have 4 cases, 3 of them for heads and just 1 for tails. Again, let's set our randomizer to 4 possible outputs, but this time we're using 2 bits to represent each outcome. To make it easier for interpretation, let's color code tails as red, which is the 0, output, and heads in green for the rest of the outputs. To generalize this encoding for any number of cases, we can analyze our previous example. For 2 cases, we needed 1 bit. For 4, we needed 2 bits. And for 8 cases, we would supposedly need 3. You might start to notice that the number of cases is just 2 to the power of how many bits we have. Using simple logarithms, we can write this out as the number of bits being log2 of the number of cases. If we generalize the assumption we made before about using binary numbers to using any base b of our choice, then the formula becomes number of digits equals log b of the number of cases. Let's project this on the scenario of equal probability for every event. This would mean that the probability of each event occurring is simply 1 over the number of cases, and vice versa. We can therefore substitute this into our previous formula. But what if we wanted our law of probability to not be equally distributed, as was the case for our unfair coin? I mean, technically we had just 2 cases, but relative to each output, we had 4. Well, one way to solve this is to simply multiply each event by how likely it is to occur, essentially p of x, and sum over all the other events. This works because effectively log of 1 over p of x is the number of digits required relative to x. Using some math, we can write it as follows, and let's label it h of x. This is called entropy in information theory. It tells us how random or how equally distributed a law of probability is. If we used entropy to calculate the number of bits needed to encode the unfair coin, we would actually get a value smaller than 1, which is far from our assumption of 2 bits. This happens because we skipped over a fundamental concept of our encoder, that is, all outputs being of equal probability. See, if you recall the randomizer we made, by labeling the outputs, we were putting another layer of encoding over them. This is actually called weighted encoding. 0.8 is the correct answer here. Although very unintuitive, if you think about it, a coin with 0% chance of either heads or tails would need 0 bits to encode. And this number grows the closer you get to an equal probable distribution, with its largest value, in this case 1, being called maximum entropy. Okay, what if we wanted to use this concept of entropy to compare our two previous coins? We said that log of 1 over p of x is the relative number of cases for an event x, using the probability law p. So by dividing 1 over p of x by 1 over q of x, assuming p is the law for the fair coin and q is the law for the unfair one, this would mean that the result is in fact the difference in the number of digits needed for encoding, if we went from p to q. Or in other words, the diversion of the law p relative to q. This in information theory is called relative entropy, or more commonly called back-Leiber divergence, or simply KL divergence for short. Question: what do you think would happen if we combine our two previous notions, that is entropy and KL divergence? Well, after some mathematical simplification, we get the following formula, which, if it looks familiar, is actually the formula for binary cross entropy. This is the function behind the string of code you write in your machine learning model's loss function, with P being the labels behind your data and Q the labels predicted by your model. And as some of you might notice, this function actually never reaches zero, because the entropy of P is constant and the KL divergence is always positive. The reason it's still used rather than simply using KL divergence, which would be better suited for binary classification, is because it is a lot more efficient when back propagating through the neural network. In other words, this is a lot simpler to derive than this. If you still struggle to find intuition behind what we just did, you can simply think of your input images as our physical coin, your randomizer as the predicted classes, and the binary cross entropy function as your model. Except your model is only able to approximate the output instead of give you exact results. So in other words, a binary classifier is simply an encoder, encoding an input vector into a binary class.